Now I don't know about you, but I've never tried to dig a hole through the earth before. Not successfully anyway. I hear it gets pretty hot down there and the chance of survival is rather low, but if you did manage to dig a nice clean hole all the way through, how long would it take you to get to the other side? Now again, no one has actually tried this, but we can work it out pretty well using some simple physics. Newton's equation for the force of gravity between two objects, say the Earth and your pet dog, states that this force is equal to the mass of the two objects multiplied together, divided by the square of the distance between their centres, all multiplied by our gravitational constant that basically dictates the universal strength of gravity. We can see that the further away we get from a planet, the smaller the force of gravity is on us. But what about inside the planet? How does the force change here? Well, imagine for a second that the Earth was just a two-dimensional circle, and that we were on the edge. Here we experience a force from every single particle that makes up every single part of the Earth. All of these forces are symmetrical about the line connecting us to the centre of the circle, and hence all the sideways components of these forces cancel out, and so the resultant force of all these forces is just one force pulling us directly towards the centre of the planet, and not to one side or another. The same principle applies when we are inside the Earth, except this time we have mass above us as well as below. When we consider all the forces from every point in the Earth, all the forces from points further out from the centre of the circle cancel out, leaving just the mass closer to the centre affecting the force of gravity. We can treat this just like if we were on the surface of a smaller Earth, so that as we fall further, the effective mass of the Earth gets smaller and smaller and smaller. Now let's return to our equation. The force of gravity equals g big M little m over r squared, where the mass of the Earth is equal to its volume multiplied by its density. The volume of the Earth is proportional to the cube of its radius, and a cube divided by a square just leaves the force of gravity being proportional to the radius of the Earth. Now because we know that as we fall through the Earth we're effectively making the Earth smaller all the time, the radius of the remaining mass decreases and hence the force of gravity just decreases proportionally. This means that our force distance graph between the centre of the planet and its radius is just a straight line. Therefore, as we fall towards the centre of the Earth, we accelerate to faster and faster speeds, but the force of gravity acting on us decreases all the time. At the centre of the Earth, the force of gravity on us is now 0, because all forces in every direction cancel out. There's no picnic break here though, as we are now travelling at our fastest speed during our journey, at around 15,000 miles an hour. This means we are going straight past the centre of the Earth and out towards the other side, which for me in Britain is somewhere southeast of New Zealand. As we do though, we are now being attracted back towards the centre of the Earth, and hence we start to decelerate, slowing more and more as the force on us gets stronger and stronger. In the end, provided that there's no air slowing us down in our tunnel, we will just make it out the other side, coming to a speed of exactly 0 as we reach New Zealand. Make sure you grab onto something quick though, as otherwise you'll find yourself falling right back down again. In fact, with no air inside our tunnel, this could continue forever. But then again, if there was air slowing you down, you wouldn't even make it out the first time, so count yourself lucky that we vacuum pumped the place first. This type of motion will be very familiar to physics students all over the world as a type of simple harmonic motion, where the force is directly proportional to the distance from the centre of the oscillation. It is the same motion that a simple pendulum undertakes, for example. It is also the same sort of motion as the orbit around a planet. In fact, if you were to look at a shadow of a person falling through the centre of the Earth and a satellite moving round it, you would see that the vertical motion is exactly the same. Because of this, we can use some simple maths involving angular velocity to come out with an equation for the time it would take to cover this distance. If this maths confuses you, just know that this is exactly the same as the time period of a pendulum, or of a mass on a spring, just with some of the constants changed. And finally, if you haven't died already from a maths overload, all we need to do now is just plug the numbers in to come out with a time of 42 minutes.